In the last video, we saw how to write statements in C. Statements could be simple statements or block of statements. Statements could also be in terms of conditional statements like if else or switch statement, and they can also be in forms of loops like for, while and do while. Statements can also be keywords like break and continue keywords. We saw all of these ways of writing statements in the last video. In the current video, on one hand we will see functions, and on the other hand we will see how to implement a functionality by breaking it down to multiple functions and how can it be useful. Lastly, we will see modular programming. So functions are the collection of statements. In part 4 of this series of C programming, we have seen more about functions. The purpose of this video is to see how to implement a functionality using functions or multiple functions. Okay, we have a problem, then we find its logical solution, then we design the solution, and then we code it. That's how we start from the problem statement and finish its code implementation. So we have this problem statement, for example, that we have to solve this equation ax plus by is equal to c. A and b are given to us, c is also given to us. We need to find an integer solution x comma y for this equation. Can we solve this particular problem? We need to understand that Euclidean algorithm of a comma b gives GCD and let it be k. Extended Euclidean algorithm gives coefficients x1, y1 also along with the GCD such that ax1 plus by1 is equal to GCD of a comma b. Right? So we write what we get from the extended Euclidean algorithm when we supply a and b to it. Now we have to solve this particular equation. So what we do is that we multiply the above equation by c upon k. We get this particular thing, and now when we compare these two equations, we get the values of x and y. We do it with the help of a flow chart. So we had a comma b, and we found x1, y1 and the GCD using Euclidean or extended Euclidean algorithm, and we see that if c is divisible by k, then we have a solution which is this, otherwise we don't have an integer solution. Okay, so before moving forward, we will quickly understand Euclidean algorithm and extended Euclidean algorithm. So I have coded over here a Euclidean algorithm. What it is, let's suppose we give two numbers a comma b over here, which is let's say 24 comma 36. Right? The smaller number comes first and the bigger number comes later, and then the bigger number is further like is done modulus operation upon by the smaller number, and then smaller number will automatically become bigger than b mod a, right? And that's how we recursively go on until the smaller number becomes 0 and whatever remains of the bigger number will return it. That becomes the greatest common divisor of the two numbers a and b. That's Euclidean algorithm. Okay. So for example, for 24 and 36, we know that the greatest common divisor will come out to be 12. Let's see if our algorithm is working fine for it or not. Yes, so we can see that our algorithm is working fine. So this way of writing a program is called recursive way of implementing a solution, right? And the function calls itself. There any algorithm which is implemented recursively could also be implemented iteratively. So we will quickly see how can we do it iteratively. We are doing b mod a repeatedly which is getting stored in A, and then A is compared for 0. So what we'll do is we'll see while B is greater than 0, we'll do B equals to B mod A, and then we are continuously getting like updating A to B, right? So we have to make A is equal to B, but here then this will become problematic, right? So we'll have to have a temporary variable which will store the value of A, and here we will be using that temp variable, right? And then whatever remains of A will be the GCD. So here we will return A. Yes, right. So that's how we implemented iteratively. The difference between recursive implementation and iterative implementation is that recursive implementation is a lot easier to implement as compared to iterative solution, but iterative solution doesn't, I mean iterative solution will be more faster and lesser memory consuming, because here whenever you call a function recursively, then the current context, the value of the current variables goes on to stack, and that's why stack gets filled up. So that is memory consumption, and then when we return, then push and pop operations from stack happens to gain back the previous values, and that results in more time. Okay, so this is Euclidean algorithm. Now we'll see extended Euclidean algorithm. So let's understand extended Euclidean algorithm. So we say that GCD of A comma B could be written as AX plus BY. Right? That's what extended Euclidean algorithm provides. It provides the coefficients also along with the GCD. Right? So we saw in the previous code snippet that GCD of A comma B and GCD of B mod A comma A, which is like the next step in the algorithm, both will give us the same GCD only. Okay, and for that the coefficients will be x1 comma y1, right? So when these numbers are changing, the multipliers or the coefficients will also change, correct? So what is happening here is B mod A could be written as B minus B upon A into A. So B mod A is nothing but you subtract from B the quotient A times, right, into x1 plus A y1, which is equal to AX plus BY, right. Now we separate x1 and y1 separately, and we get the value of x and y. So we can say that x equal to y1 minus bx1 by a and y equal to x1, meaning to say that when we go on to compute, so we'll understand it from this diagram. From GCD of A comma B, we go on to GCD of B mod A comma A, and we further go down to GCD of smaller values. We get GCD at the end, and for that x equal to 0 and y equal to 1. Just keep the recursive solution. Okay, so here I am returning B. B is the coefficient of y, right? Or y is the coefficient of B. So at the end we get y equal to 1, x equal to 0, and from there onwards start building the upper coefficients, right, using this relationship, and at the end we get x comma y. So that this is extended Euclidean algorithm, right. We can just modify this. go back to a slide and we will say that x equal to y1 minus bx1 by a star x is equals to y1 minus b into x1 by a, and star y is equal to x1. Then we return GCD. Addresses of the two variables. Some mistake we've done. Okay, here we have not given the values of x and y. Yes, so here we get minus 1 comma 1. So 24 into minus 1 is minus 24 and 36 into 1 is 36, and when we add them we get GCD, right? So we get x and y. Now we have another variable k as this thing. We can write if k if so we have, let's say now we want to solve ax plus by. We have a as 24, b as 36 and c as, let's say, 24 only. Okay, yeah, I can do. Yeah, so I get the solution, and else, right? So if I make c as not the multiple of k, then I'll get that the solution doesn't exist, and I'll have it as backslash n here, so that it prints, yeah, the solution doesn't exist, right? So now I have implemented this functionality by breaking it down currently into two functions. Further do is I can have this thing into another function. This is our main driving function, right? It is not doing any calculation, it is just uh, like having the inputs and then just sending the inputs, and it is just printing, right? So this calculative part, for again we can have a separate function. We can call that function straight away from here itself. So c k x and y. Yes, let's see if our code is still working fine. Yeah, the solution doesn't exist, and let's say if I have it as 120, so 24x plus 36y is equal to 120. Let's see what is the solution of it. Yeah, so as you can see, we have broken it down to very small micro functionalities wherever we can. Now we will look into design, the important concepts of design. So it's important to break down the implementation in multiple small functions, and functions should be performing atomic operations only. For example, one of our function was only implementing extended Euclidean algorithm. One function, which was main function, was only driving the inputs and calling the functions, right? And then that solution check functionality was only checking whether the solution is existing or not, right? So when we break down the bigger functionality into smaller functionalities, it has multiple uses, and we'll see what are these uses. So firstly, it helps us in defining very specific functionalities. I have three functions, and each of these three functions have this work to do. Okay, it is further helpful in testing. So when the functions are individually tested, the tester knows that okay, the input to these functions are, let's say 3 or 4 inputs are there and one output is there for this function, or sometimes there is no output, and this particular function just performs this particular task, which is, let's say, just calculating uh, the greatest common divisor or just checking whether the solution exists or not, right? If we implement everything in just one function or a lot of things in one function, then it will be difficult to determine the behavior of the function, and then writing test cases for it could be little complicated, right? When we have small functions, okay, right, like functions implementing atomic functionality or just a single functionality, then design will be much more granular. In design there will be more clarity and more depth, right? For example, if we have just one function, right, implementing 4-5 things, and another function implementing another 4-5 things, and then in design when we like show these two functions and try to explain it, that detailing will not come. But when you have multiple small functions and then in design you explain the functionality using those small functions, then there will be greater granularity and detail in designing, which is considered to be a better detailed design, right? Another point is, like, you might have seen in the code implementation that I have local variables, and then I am passing the address of the local variables to compute GCD function by ampersand x and ampersand y. That is because the we are uh, finding three uh, we are calculating three things from the compute GCD. What is those? The coefficient x, coefficient y, and the GCD. But the function can only return up to one value. So we have returned GCD, but for the other two x and y, we update on the address. So when the address is updated, you can access the updated value from anywhere, right? You don't necessarily have to be dependent on the return keyword. That is another observation. And finally, like, variables and function names have to be meaningful. You can't just write x, y, or z, or name of the function as something random, because later on when we see the code it should be meaningful. Let's see what is modular programming, right? If you want to savor the taste of mango, just if mangoes are there, just have it. Don't think too much how they are grown or how they are planted and all that, right? So modular programming is this only. It is just like an API. When we have API, we just need to know how to use the API, not how the API was implemented and all the details. For example, we have printf function, right? We just know how to use printf function by, like, %d if we want to, like, have some integer value printed and all that, right? We are not concerned how printf is implemented. So we can also have this interface implementation modular programming thing, this, let's say, compute GCD functionality. Okay, now let's say compute GCD functionality is used at multiple places in multiple .c files in your big code. So what could be done is, this could be just implemented in another .c file, like I have done over here, and a .h file could be created where we declare it as an extern. That particular functionality we declare it as extern, right? So I can just remove this functionality from here, and I will just include the .h file, extecu.h, right? And now also my code should work just fine. Wait, so here I am using wrong instruction to compile, because now I have to compile that .c code also where my functionality is written, compute GCD functionality, right? So along with this instruction I will have cu.c also. So this is the instruction which will compile all the .c files, and finally everything will be there in this object file. So as you can see, now also it is working fine. So to summarize, what I have done is I have written that functionality over here, and I have provided an interface into this .h file. So when this interface is provided, that interface I can just include over here, and then straight away use the interface without worrying about its implementation. So let's say if my application have hundreds of .c files, and in 5 or 10 places I am using compute GCD functionalities, so I can just use hash include this particular .h file everywhere where I am using this functionality, and it should be just fine. So there is one question for you. Why do we have to include .h file? Why can't we straight away include .c file? So if you know the answer, you can comment it, or if you want the answer, then also you can comment it. Video, we'll look into the control flow concept in C, and inputs and outputs to a C program in terms of file or command line input outputs. Thank you. Hit like if you found anything of value from this video. Thank you.